third lesson of 4 from Unit 7. We're going to kind of take a break from areas under curves. Okay? Time out. Start over again. This is completely different for right now. Okay? Antiderivatives. We're going to kind of stop area, leave the whole area realm. We're going to go into antiderivatives, and the key is the last lesson will kind of tie things together. But for today, you don't know how it's tied together. You just need to learn what an antiderivative is. Okay? So we know how to take derivatives. We should know how to do all these. Derivative of 6 is what? Derivative of 4x plus 2. X cubed. What would be this one? Derivative of the sine. What rule? We have to use 2 rules. Do we have to use for x to the 5th sine cubed x? Product and change. So we got the derivative of the first times the second. What is the derivative of sine cubed of x? 3 sine squared x times cosine x. I heard a couple people say it. So this is sine of x to the 3rd power. The derivative would be 3 sine x squared, or 3 sine squared x, times the derivative of sine x, which is cos x. Okay? And then last 2, we have the quotient rule. Okay? Secant squared x, e to the x plus derivative of e to the x, e to the x, tan x all over e to the x squared. What's up? Minus, not plus. Thank you. F prime g minus g prime f all over g squared. Cool. So pretty much any function we can take the derivative of. Great. Well, let's see if we can go backwards. I'm going to give you the derivative. You tell me what the function is. It's almost like I give you the answer, you give me the question. Okay? Go backwards. The derivative is 4x. What was the original function? You guys figure these 3 out, compare with neighbors. What function, when I take the derivative of it, is 4x? What about same thing for x squared? Then the same thing for cos x. Okay, looks like a lot of us got the top one. I see a lot of people write 2x squared. Mr. Russo, you got 2x squared? Good. Mr. Grubke, get that? All right, Mr. Gordon. What about the second one? What function's derivative is x squared? 1/3 x cubed. Interesting. Definitely correct. Now, you just think about it. X cubed, the derivative of x cubed, if I went like the other way, maybe I'll go this way, is 3x squared. But we just have x squared, so I need to kind of account for this 3, which is why I have this 1/3 here. Okay? Then what about the last one? Negative cosine x. Good. Okay, all good answers. Did anybody have any other answers, say, for the first one? Because I'll tell you there are other answers. There are other answers for the second one, and there are other answers for the last one. Anybody think about any other possible answers for any of those three? All right, it's going to blow your minds. Ready? Well, right, isn't the derivative of 2x squared plus 5 4x? Yep, and the derivative of 1/3 x cubed plus 2, that derivative is x squared. Derivative of negative cosine x plus 1, that's sine x. So, you know, we could have any number here. It does not have to be 5 or 2 or 1. It could be any positive, negative number. It could be pi. It could be e. But all of a sudden, you know, we got to think about that as well. So actually, though you have a correct answer, the most correct answer would be this plus some constant. And C could be 0, it could be positive, it could be negative, it could be rational, irrational, it doesn't matter. But right, because the derivative of a constant is 0. The slope of a horizontal line is 0, so we have to take into account that. Okay? All right, those are 3. Do we have any more? Okay, this one. Do this one real quick. All right, what do we get? Anybody? Isn't it just 1/3 x cubed and then negative cosine x? Is that right? Why isn't that right? Yeah, because then I took the derivative of the product rule. Well, it's not as easy as taking derivatives. Okay, there's actually a rule. If you're a BC student, you will have to know how to take the antiderivative of this. If you're an AB student, you won't. Now, it's a technique, and you'll learn this technique in the future. But these techniques are, you know, more complicated than like a derivative rule that you already know. So taking antiderivatives not as simple as derivatives. I could have given you any function up here. You would have been able to take in the derivative. You pretty much know all the rules for derivatives. Antiderivatives not as easy. Okay. All right. Let's define what an antiderivative is. It's really not necessarily a definition. I'll just say like f of x is the antiderivative of f prime of x. Now, the antiderivative of regular f is big F, capital F of x. Okay? We could say f prime is the antiderivative of f double prime, so on and so forth. But we usually do not stop. We usually stop with this big F. We don't use like big F squared or big F cubed or anything like that. We would just define other functions. Instead of like with derivatives, you do like f to the fourth, and that's like the fourth derivative. We would not do that with antiderivatives. We kind of just stop here. Okay, make sure you account constants if we go backwards. That's one important thing. And let's just start with our basic antiderivative rules. Okay, so this is rule number 1. If f of x is equal to 0, big F of x, or its antiderivative, would be equal to what? C, 0, 5, 12, all of those numbers The derivative of a number is 0, so this would just be a constant c. Your second antiderivative rule. If we have a function that's equal to a constant, say if a function is equal to 5, its antiderivative, what is the antiderivative of 5? What function has a derivative that's equal to 5? 5x. Good. So this is 5x plus c. If it was a constant k, we would say this is kx plus c. The power rule. We already did this one. Let's change it up since we already did x squared. Let's change it to x to the 4th. Okay, if I have a function, x to the 4th, and I want to try to find its antiderivative. Well, we know that something to the 5th power will have a derivative that's to the 4th power. Okay, so x to the 5th is where we're going to start. But we know that the derivative of x to the 5th is 5x to the 4th, not just x to the 4th. So I need to kind of account for that. So what I need to do is multiply this by the reciprocal of my new exponent. And this is the antiderivative. If I take any function, 1/5 x to the 5th plus a c, take the derivative, I'll get x to the 4th. How can I write that out just generically?
1 over n plus 1 times x to the n.
Exactly. 1 over n plus 1 times x to the n plus 1. The way I like to do that is, or say that, is add 1 multiplied by the reciprocal. Add 1 to the exponent, multiply by the reciprocal of your new exponent, not your original. Plus c, of course, plus c right here, and plus c right here. Okay, now, before we do these 3, we need one more rule. Rule number 4. If my function is a constant times another function, we can just pull out the constant and multiply the constant by the antiderivative of my function. I would say big F of x would equal to k separate from the big G plus the c. That might not make sense right here, but when I do this first example, you'll see why we talk about this. Okay, so first example using this power rule. We have a couple examples using the power rule. And this is definitely the most important antiderivative rule that you'll see, this power rule. If I want to take the antiderivative of 1/3 x to the 4th, or if I want to find big F of x, I'm going to leave the 1/3 off to the side, and I'm just going to worry about the x to the 4th. So if I want to take the antiderivative of x to the 4th, I did that up here, that would be your exponent plus 1 times the reciprocal of your new exponent. Well, now I can take this 1/3, multiply it by the 1/5, I get 1/15. Okay? You guys do the next two. I'll actually add a third one just for practice. Check your answers with your neighbors. Check your answers. Don't forget your plus C's. Okay, add 1, multiply by 1/4. That's 6 times 1/4 plus C. So that's 3/2 x to the 4th plus C. Add 1, you get -1 multiplied by the reciprocal, -1/3 x to the -1st plus C. This is an exponent of 1. Add 1, you get 2. Multiply by 1/2. You have 4 times 1/2 x squared plus C, or 2x squared plus C. How can you check to see if these answers are correct? Take the derivative. After you get every single antiderivative, you should be thinking, all right, if I took the derivative, 4 times 3 over 2, that's 6, x cubed, check. Okay? Couple more. If we are adding multiple functions together, so this is an example of adding multiple functions together. So g plus h plus maybe like a k, whatever. Could be however many functions you want to add or subtract together. The antiderivative would be considered the antiderivative of the first plus the antiderivative of the second, and so on. Simple. That's big K. It's tough to show big K. So just h of x plus or minus ... plus c. Okay. Go ahead and find big F of x if f is this. 5x cubed plus 12x squared plus x plus 3. Very good question. We'll talk about that. Just write down what you think is the answer, and we'll talk about possible C configurations. Add 1 to the exponent first, then multiply by the reciprocal of your new exponent. So if you got x cubed, add 1, that's x to the 4th, multiply by 1/4. Now, let me show you a possible way to write the answer. So this would be x to the 4th times 1/4 times 5, so it just becomes 5/4. And then the antiderivative, I've been saying you got to add these plus c's. So I put a plus c there. Then I have x cubed times 1/3 and then 12, that's be 4. And then I say, okay, add the plus c. And then I say x, well, that's 1/2 x squared. That's a plus c. And then 3x plus a c. What do we think? Do I need all those c's for every single one? Why not? Yes. A c is just a number. Another c is just another number. Add all these c's together. What do you have? A c. Another c. So this is why we just have one c up here, and I don't have a plus c in between all the h's. Okay? So this is just equal to c. So that's why we'll just have 5/4 x to the 4th plus 4x cubed plus 1/2 x squared plus 3x plus c. Okay. Trig rules. Well, as long as you know your derivatives of your trigs, you'll know the antiderivatives. The tricky thing is with our pluses and minus signs. So if our function is sine, what would be its antiderivative, big F of x? Negative cosine, exactly right. So the derivative of sine is cosine. Now it's flip-flopped for antiderivatives. Next one is cosine. What is its antiderivative? Sine. Yeah, it's almost like I'm giving you the answer. You have to produce the question. Anybody remember the function whose derivative is secant squared? Tangent is correct. What about the function whose derivative is secant tangent? Secant is correct. What about the function whose derivative is cosecant squared x? Yes, it would actually be negative cotangent. The derivative of cotangent was negative cosecant squared. So you got to go the other way with positive cosecant squared. And then positive cosecant x cotangent x. The derivative of cosecant is negative cosecant cotangent. So this would have to be negative cosecant x. Notice how specific these trig rules have to be. It's not like I gave you this. What function has a derivative that's equal to tangent? Something, exactly. We don't know. We don't know what this is. We'll be able to find this soon. Well, not that soon, but eventually. This is difficult. I can't just pick any random trig function. Like, I don't have cosecant here. I don't have secant here. I really have the specific ones that I know from my derivative rules. So this is hard, even just finding the antiderivative of tangent. What about sine times cosine? Right? This is hard too. Antiderivatives are tough. There's these specific techniques that we'll learn. It's not a rule, it's a technique that will help us find antiderivatives. But for now, it's just kind of like, I'm not sure. So don't be discouraged. All the problems you're going to be given, you're going to be able to find the antiderivatives. And if for some reason I give you a problem where you can't figure it out, then that's mean. That's all I can say. All right, notation for antiderivatives. There's a specific mathematical notation for finding an antiderivative. I've been just giving you F and asked you to find big F, but there's a specific notation for taking an antiderivative. Okay, first, reminder. What is the notation that we use for taking a derivative? d dx is correct. This notation means take the derivative of 3x squared with respect to x. Okay? And what do derivatives give us? If I plug in values into slopes and tangents. So we know what derivatives give us, instantaneous rates of changes, okay? Right now we don't know what antiderivatives give us. We just know what they mean. It's just the function whose derivative is what we started with, okay? Well, the notation for the antiderivative might kind of make our gears move in our head a little bit. So that's the notation for taking the antiderivative of 3x squared with respect to x. So you can assume right now that areas and antiderivatives are related, right? That's all you can assume right now. You probably don't even know why or how, but we'll talk about it next class. Okay? This is confusing to a lot of students, and you really have to understand how this is different from this. These two things are different. This, in this situation, means take the antiderivative. This is our infinite sum notation from A to B. This, if you're taking your infinite sum of your really, really skinny rectangles, represents the area, right? Well, without the A to B, it stands for antiderivative. Okay? Just go with it for now. We'll find out the connection next class. So, here are some examples using this antiderivative notation. The first one's probably the trickiest one. If you don't understand the first one, do the second and the third. Mr. Messner. That was last period. Yeah, no problem. Okay. This right here means take the derivative or the antiderivative with respect to x. Take the antiderivative. Now the middle one, this is x to the 1/2. Add 1 becomes x to the 3/2. Multiply by the reciprocal, x to the 3/2 times 2/3. Let's see. Okay, do the last one. X to the 5/2, add 1 becomes x to the 7/2. Multiply by the reciprocal, that'd be 2/3 times 2/7. That's 4/21. X to the 7/2 plus AC. Questions about those two? Add 1, multiply by the reciprocal. What is the answer to the first one on the left? X plus C is correct. Good. There's a 1 hiding there that's being multiplied by dx. Okay, lots more. You have a power in the denominator, rewrite. This is kind of like going back to day 1 when I first taught you the power rule for taking derivatives. I said don't use the quotient rule because you don't know the quotient rule yet. Instead, rewrite everything. Well, we're going to rewrite stuff for antiderivatives as well. This will be rewritten as the antiderivative of x to the -3rd dx with respect to x. This will be written as the antiderivative of 10x to the -4th with respect to x. The same antiderivative power rule applies. Add 1, multiply by the reciprocal of your new guy. Questions about those? Okay, more things to be prepared of. If you have a polynomial, break them up into individual fractions. It's really the quotient of polynomials, not just polynomials. Polynomials being divided. Yeah, so this dx should be out here, and it should be this. So this integral notation, as it appears there, should be read the antiderivative of this function with respect to x. How do we break up into pieces? We divide our numerator by our denominator. So we have multiple fractions. This is 3x squared plus 2 over x squared. And then, of course, I would rewrite 2 over x squared as 2 times x to the -2nd. X cubed plus -2x x to the negative first plus c. The other one would be written as x to the 1/2 plus x to the negative 1/2. Take the antiderivative of that with respect to x. Add 1 to 1/2, 3/2. Multiply by the reciprocal. Add 1 to negative 1/2, positive 1/2. Multiply by the reciprocal. Okay, so now we are ready to handle those. So you have stuff that looks like this. And really just all of these, attempt to simplify first. Don't try to take this antiderivative as you see it. Instead, rewrite it. Maybe sine over cosine times 1 over cosine. Maybe the trig will pop up where we know this antiderivative rule. Derivative of secant, the secant tangent. The one on the bottom, distribute everything. Oil stuff out before you try to take the antiderivative. Questions about those? All right, good. Other ways you can be asked these antiderivative questions. Well, intro to differential equations. Calc 3 typically is just differential equations. All you will be doing in Calc 3 is solving more complex types of these situations. What is a differential equation? It's an equation that involves derivatives in x and y. It's really a tough way to explain it. Really, it's the solution to a differential equation that's important. A solution to a differential equation is an equation. Not like a number, like in algebra. It's an equation, and it's an equation that will satisfy all of our conditions. Okay, here's your first differential equation. All you'll be asked to do is solve the differential equation. If you don't know what to do, it's going to be tough. Okay? If you don't know what you're looking for, what you need to find, it's going to be confusing. But all this is saying is find, I'll write it in green, find the f of x that has these characteristics. My function has a derivative that's 8x cubed plus 5, and I'm told a point on my function, f at the x value 1 is equal to negative 4. Okay, step 1 is to find what is considered a general solution. A general solution would just be the function whose derivative is 8x cubed plus 5. That'd be 2x to the 4th plus 5x plus c. Let's consider the general solution. Like in general, it could be this. But we would use this information to find my specific solution. I know that f of 1 is equal to negative 4. Well, if I plug in 1 everywhere, I'll be able to find this c value, what it actually is, and all of a sudden I have a very specific solution, and I have found my function who has these characteristics. I get negative 4 is equal to 7 plus c. C is equal to negative 11. And this function, 2x to the 4th plus 5x minus 11, that's my particular or my specific solution. So all you got to do is really find the c after you find the antiderivative. Okay? Your turn. Solve this differential equation. Help each other out. See if you can figure it out. The key is every antiderivative you take, you need a plus c. So if I find f prime of x is 2x plus c. Guess what? You got to find that first c before I go all the way up to f. Because if I took the antiderivative of this, yeah, I have x squared, but I have plus the cx and plus c again. And I can't add these two together. So back up, find this c first. I know that the derivative at 0 is 1. Well, that gives me this first c. Now I have a specific derivative equation that will help me find my specific original equation. Working backwards. Okay? Let's go on to straight line motion. Okay? Derivatives. If I take the derivative position, I get my velocity function. If I take the derivative of my velocity function, I get my acceleration function. Well, antiderivatives would go the opposite way. If I took the antiderivative of my acceleration function, I would get a generic velocity function. If I took the antiderivative of my velocity function, I would get my position function. Should make sense, right? Well, that's the key to the connection between areas under curves and antiderivatives. You might not be able to see it today, but you'll be able to see it next class, okay? So just understand the way things work. You could have a specific question. What is the position of a function? What is the position function of a particle whose velocity is equal to t squared and whose position at time 0, x of 0 is 5? You can start working the other way. If I want to find the position function, I have to take the antiderivative of velocity. Derivative of position, the instantaneous rate of change of your position with respect to time, that's velocity. Derivative of velocity acceleration, going backwards. So I would say x of t would be 1/3 t cubed plus c. X of 0 is 5. I get my position function. Okay. Well, given this position function, I can enter in information to find out more positions. I don't know what this question is asking. What is the position of this object after 5 seconds? You plug in 5. I'm not sure if that's helping us. Oh, never mind. Here's the question. Okay, so what's the position of the object after 5 seconds given a velocity and initial position? You'd first have to find the position function. This is supposed to be a t. Amateur hour over here. This is t squared plus 3t plus c. I know the position at time 0 is 2, so that means c is going to be equal to 2. Well, I can use this particular solution to find my position at time 5. Okay, all kind of the ideas with these types of problems. 25 plus 15, 40 plus 2, 42. All right, that's pretty much it. I'm going to look and see if there's more problems, but I think we did a good job. The connection will come next class. The homework is longer than the homework that you've had over the first couple days, okay? So welcome back.